In this video, we're going to be discussing some alternatives that are available within k-means clustering, both for our distance formula within k-means and other clustering algorithms, as well as alternatives clustering algorithms to k-means clustering itself. So let's start with the distance measures. We'll talk about three alternate options, the first of which is squared Euclidean. So we have the regular Euclidean distance formula that is the square root of a squared plus b squared when we find that actual distance between the two dots. But if we square the Euclidean distance formula, we don't have to include that square root component. Now this does actually change the distances, but what's interesting about this is for an algorithm like k-means, the squared Euclidean distance is going to give us the exact same determination as to which cluster a particular point belongs to as regular Euclidean distance. And so this doesn't actually change the solution in k-means clustering at all. It just makes the algorithm a little bit faster. So you'll sometimes see squared Euclidean. Sometimes this is used within something like hierarchical cluster analysis, and that can have a bit of a deeper impact on the algorithm. But in k-means, squared Euclidean is primarily used to speed up the algorithm a little bit by making each computation a little less intensive. Manhattan distance is one we've talked about before, and that is the distance between 2 points if you're traveling as if you're traveling on city blocks, where you can't necessarily go diagonally, you have to go just horizontally or vertically. Ultimately, the distance between 2 points when you do that is the sum of all the horizontal distance plus the sum of all the vertical distance, and that's really it. So Manhattan distance is just a plus b in our Pythagorean theorem notation and can be pretty handy in its usage. The supremum is a third type of distance, and this is where you use either the maximum of either the horizontal or the vertical distance between 2 points to calculate the distance. So instead of adding, say, the horizontal and vertical distance together, or squaring the horizontal and squaring the vertical and then adding them together, or squaring the horizontal, squaring the vertical, adding them together, and then taking the square root, instead you just look which one's bigger, the horizontal or the vertical, and then you just use that distance to define the distance between the point and another point. So all three of these are potential alternates to the Euclidean distance metric. All three of these have different potential benefits and detriments. We did introduce Manhattan within this lecture set as an alternative to Euclidean distance when you're looking at lots of variables and are worried about the cursive dimensionality. And squared Euclidean also, clearly comes into play if you're just looking to speed up the algorithm. And in fact, probably squared Euclidean would be the default because it gives the same output in k-means as Euclidean, and it's faster. So why not use it if it gives the same answer? So that's the reason I included, is so that if you see it, you know, hey, it's the same thing as the distance we've been talking about. It gives the same answer. Though in our class we focused on the more intuitive Euclidean distance. Well, while there's been alternate distance options, there's also alternate algorithmic options. K-median and K-mode. So in the same way that we have K-means, where we find the mean x and the mean y to find the centroid, you can do the median x and the median y to find the centroid, or the mode within each group. And for these, k-medians can be useful when there's outliers in the data, of course, but k-mode is a really interesting one. The video for this lecture set uses k-mode, and the speaker in that video discusses that briefly, but doesn't discuss the reason. So the reason that the speaker uses k-modes there, and the primary usage I have seen of k-modes, is when our data are categorical. That is, when I can't actually calculate a mean of the data, I just have the categories. And in that particular circumstance, calculating the mode makes a lot of sense. We discussed hierarchical clustering, and previously I think I mentioned we're going to come back to that. So we're going to discuss what actual hierarchical clustering does and how we can interpret this, including the dendrogram, which is the big piece that we're going to take away from hierarchical clustering if we're trying to determine the number of clusters for, say, a k-means analysis. A third option is maximum likelihood, or combined with the EM algorithm, EM standing for expectation maximization, which is a way in which we can approach a situation where we're not really sure. We're trying to determine both distributional properties and clustering properties, and EM is actually a fantastic approach for this. And ultimately, our goal is to maximize the likelihood. Now, you've probably seen maximum likelihood elsewhere. Maximum likelihood is an extraordinarily general approach. And in fact, EM is also an extraordinarily general approach. And you can see both of these used in a variety of different contexts, including regression, factor analysis. We've got it obviously today in cluster analysis. There's a bunch of different places that this can happen. And it's one of the reasons I kind of like maximum likelihood. Plus, I think you'll like how the image looks. We also have a mean shift algorithm. This is kind of an interesting approach. I really like how it works. And actually, there's an individual approach, what each individual point does, but then there's the group approach, which is very, very cool. I quite like it a lot, and we'll discuss it. And then finally, we have a DB scan approach. Now, I should say, I actually didn't make any of the graphics that we're going to see. They're pulled from this particular website, which also discusses some of these details. So I'd encourage you to go check it out. They're pretty cool. Honestly, the reason I pulled these among all the others, they are pretty common in my experience, but the reason I pulled them is because they had cool graphics available on the website I was looking at the time. So please don't take this list and think that it's in any way comprehensive or represents the only clustering options you can do. It does represent some common ones, some cool ones, but there's always new options being invented, and I encourage you to check that out, more modern options, if that's something that you're interested in pursuing. But this should give you a good feel and fundamental. And another thing that I like about this particular mix of options is that within this particular mix of options, you're seeing a lot of different types of approaches. And more than anything else out of this section, what I want you to get a feel for is A, how frickin' cool these are, and B, the different types of approaches that they are, to just give you an inkling of what I mean when I say a different algorithmic approach, and just how creative some people can be with their approaches here. And maybe if you enjoy this, how creative you could be with an approach that you could come up with. We're going to start out with hierarchical clustering, and I'm skipping k-median, k-mode because they really are exactly the same thing as k-means, but hierarchical clustering is a bit different. So in hierarchical clustering, first of all, we should note this is very commonly used. I think k-means is far and away the most commonly used, but in the case where you don't know the number of groups, I think hierarchical clustering is very commonly used, and I think our approach, when we don't have the scree plot available, of using hierarchical clustering to figure out the number of clusters and then feeding that into k-means is also a common approach. Now, hierarchical clustering really just combines pairs of points. We'll see a graphic in a second, but it really just takes a pair of points and combines them together, which is that's it. It kind of starts, instead of starting from centroids and trying to classify all of the data points at once and slowly classifying better and better and better, it just says what are the two closest data points, and then I'm going to merge those two data points together, and keeps doing that over and over and over again. Now, there's several ways to merge, and think about if I have two close data points and then I quote unquote merge them into a cluster. How do I find the distance between that cluster and a third data point? And you could use the closest dot in the cluster to the data point. You could use the furthest dot in the cluster to the data point. I like the mean. That's what our graphic is going to show, where you see the two dots. You kind of take the average of them, and that calculates the quote unquote mean of those two dots, and then you find the distance between the centroid of the cluster and another dot, and that's how you combine the pairs of points. That kind of makes sense to me. But it is worth mentioning that there are several ways to perform that merge and to calculate those distances, not just in the distance formulas, but in terms of within a cluster, how do I calculate the distance between a small cluster that I have over in a corner, and a new data point that hasn't been assigned a cluster yet. Do I use the centroid? Do I use the closest data point in the cluster to the data point in question? Do I use the furthest data point in the cluster to the data point in question? How do I define that distance? There's a big difference from k-means. And again, that is, we don't know the number of clusters ahead of time, and we don't need to. We don't have to assume that we're right in that. And similarly, the other big difference is that we don't end up with groupings in the same way. That is, at the end of k-means, I have one cluster and a second cluster, and for every data point, I know which cluster they belong to. But in hierarchical clustering, it's just not that way. We don't end up with those groupings by default. I say we need an additional statistic. The dendrogram helps, and dendrogram from dendron in Greek, meaning tree, and gram, meaning like a drawing or a math chart, a math figure. Now, dendrograms are helpful in determining the number of clusters, but even in there with hierarchical clustering, we can determine the number of clusters and even the cluster assignment, but that's not really the strength, in my view, of hierarchical clustering. Hierarchical clustering, determining the number of clusters, is the big thing that I like about it, because again, it kind of slowly evolves. All right, well, let's look at a picture here. And I want you to see how, as the algorithm develops, I'm taking the closest 2 points at any given time and combining them. And after I combine them, that new cluster that those 2 points make, that new cluster is then treated as its own point. So in this cluster 1, I can then combine it with point 4 and it becomes cluster 2. Here I can combine 3 and point 0 and make cluster 4. So here we're treating the center of those clusters as themselves a new data point that can then be combined with other data points. And that's really the algorithm. That's kind of it. And again, it's very simple in a similar way to k-means, but it's a very different approach than k-means. And again, you'll note kind of the bottom two, or the bottom second to last bullet point, we don't end up with groupings in the same way. We just end up with bigger and bigger and bigger clusters. And the question comes, well, what do I actually do with that? And that's a really good question. So let's dive into this dendrogram plot that we haven't looked at yet, but is based on the image that we just saw, as to how we can work with this a little bit. So the dendrogram is built based on these clusters. Ultimately, the dendrogram is going to be written in terms of each of the data points, and it's going to look like, if you've ever seen like a playoff bracket in basketball, it's going to look a little bit like that, where 2 points meet and then they kind of have two little lines go up and join together to show where they become a cluster. Now, the higher the lines join up, the more space or distance was accounted for within them. So what we end up looking for in a dendrogram is vertical space. And ultimately, within that vertical space, we make a horizontal cut at a particular height. So I'm looking for vertical space, and I make a horizontal cut. Now, when I make a horizontal cut, I'm going to cut across some lines in my basketball bracket. And when I cut across those lines, each line that I cut across represents a cluster that is recommended to be included. So I'm going to find the biggest chunk of vertical space I can where there's no breaks, that is, no clusters being created. And I'm going to draw a horizontal line within that space. And as many vertical lines as that horizontal line crosses, that's going to indicate the number of clusters. And these big vertical gaps provide a good quote-unquote solution in terms of the number of clusters. So all of this sounds a little theoretical. Let's look at how this dendrogram is built side by side with that hierarchical cluster graph that we just looked at. So on the left is the graph we just looked at. On the right is the dendrogram. And you can see that horizontal line at that particular point indicating 5 clusters. Here, a horizontal line indicating 3 clusters. Now we have another horizontal line indicating 2 clusters. So that's what we mean when I say the horizontal line. Look at how many vertical lines that horizontal line ticks past. You see that was 5 vertical lines it ticks past. Here it's 3 vertical lines it ticks past, so it indicates 3 clusters. There we have 2 vertical lines it ticks past, 2 clusters. Now in reading this, I don't start from the bottom. That is how the chart is built, but that's not how I read and interpret. I actually start from the top because I want big clusters with lots of data points, not little clusters with just a couple of data points. So I might start at the top and read down in 2 clusters. There seems to be a reasonable amount of vertical space between that and where it breaks into a 3 cluster solution. That is, the point 3 combines with that red cluster. And so I might interpret that because there's a good amount of vertical space with 2 clusters, this might be a 2 cluster solution. Of course, I might look down and say there's a good amount of vertical space with 3 clusters. Maybe this is a 3 cluster solution. And I might equally look down and say, hey, there's a pretty good amount of vertical space with 5 clusters here too. Maybe this is a 5 cluster solution. So each of those, and you're seeing those highlighted on this particular plot here, going in the opposite direction that I would read this because it's building up from the ground up. Each of those could be valid interpretations of this plot, where I think this could suggest a 2 cluster solution for the original data, potentially a 3 cluster solution, and potentially a 5 cluster solution. And if it's a 5 cluster solution, what you'll see when the graphic pauses, and we'll wait for it to come back around, but if it's a 5 cluster solution, you can actually see on the left graphic, if you pause the videos, what those 5 clusters would be. So you can pause now, and then you would have seen what those different 5 clusters were. Right. Let's move on to the next one, maximum likelihood. Now, I'll be 100% honest with you. The graphical representation of the maximum likelihood on that website is the whole thing that gave me the idea for this part of the lecture set. I really, really like it. And the rest of the videos here and the images that we're looking at, I think, are very helpful. And I think it's great to be able to learn and understand a little bit about what's going on with the different ideas. But this particular graph, I really, really, really love. As we talked about earlier, EM is an algorithm, and maximum likelihood is an optimization. We're maximizing a likelihood function or a log likelihood function. And both of these are much broader than just clustering in general. So it's worth mentioning that, like, again, these things are not just for clustering, I guess is what I'm trying to say. These are broad approaches that can be applied in the world of clustering, but certainly aren't limited by it. So you'll see maximum likelihood for regression, you'll see maximum likelihood for factor analysis, you'll see maximum likelihood for clustering, you'll see maximum likelihood in a bunch of different areas. Same thing with the EM algorithm. And understand that the use of these within this context is simply using a broad theoretical approach within this particular context. Incidentally, that is the strength, is that this is a broad theoretical approach that's used in a variety of different areas very successfully, and we just seek to maximize the probability of the data. Now, what's interesting about this, it's actually very similar to k-means in terms of the steps, but instead of assigning one particular group to a data point, we assign the probability of one group versus another. So we have some shades of gray here in a very similar way to logistic regression, which, depending on where you're at in the course, we may have already talked about. But in logistic regression, we don't predict a binary outcome, a 0 or a 1. In logistic regression, we predict a probability. It has some shades of gray in there. And in a very similar way, the maximum likelihood or the EM algorithm approach to cluster analysis does the same thing. This is pretty handy because it allows for expressions of probability in terms of how much we believe a particular data point is associated with a particular classification. So we might feel very strongly or believe with a very high degree of probability that a particular data point is associated with a particular cluster, but maybe with another data point, we don't necessarily believe, maybe that cluster is the closest, but we're not really convinced. And through maximum likelihood in the EM algorithm, we can actually express this. And again, it just makes a really, really cool graph. So I encourage you to take a moment and just check this graph out to see what different iterations of this algorithm look like. Note that for each of the colors, the different shades of the color represent different shades of probability. So the lighter version of the color represents lower probability of being involved in that group. The heavier versions of that color represent a heavier probability of being in that group. And what really feels like it's happening here is almost like a magnet effect, where you see that blue and red start out in the same cluster, but as the algorithm continues on, blue starts to be drawn to this cluster that hasn't really been well captured in the solution yet, and ultimately gets pulled over as if it's like a magnet, or like, I don't know, like putty or Play-Doh or something. It gets kind of dragged over in that section, and then that nice final cluster solution does seem to represent the data points pretty well. But again, you'll see that there's some edge cases, especially in the red group, where red might be the best thing, but maybe we're not quite sure. Specifically in the red and the blue group, and some of those middle data points, it really does do a good job of representing the fact that those are kind of edge cases where these clusters do seem to be crossing over, and there may be varying shades of probability that those data points are associated with either the red or the blue cluster. And again, this is a benefit to the maximum likelihood approach that we have that probability. Now, one of the things that is the problem with this is we do make some distributional assumptions regarding the data. That is, we do have some normality assumptions that go behind these dots, specifically some joint distributional normality assumptions. Obviously, that blue graph is not just normally distributed and perfectly in both directions, but you can see in the joint distribution, that is, in the angle that it represents, if you projected that down to either the horizontal or the vertical axis, that would be normally distributed. So these are, we do make some distributional assumptions with this, and that is one of the limitations within this particular algorithm. Now, if you had a different likelihood function that maybe wasn't normal distribution based, you might be able to approach this differently, but either way, you're going to need to come up with a likelihood function, and that involves making some assumptions about the data. So it's a big limitation here. Otherwise, though, I think this algorithm is pretty cool, and again, makes some pretty cool graphics. All right, mean shift. So if the last image was kind of like a magnet pulling that circle from one cluster to the next, this approach is going to remind me a lot more of a black hole. So let's talk about the algorithm for a single dot. So we'll look at a single point that represents, and just roll with me on this. It's not necessarily a data point, but it's kind of a middle point that we're going to let find the middle of clusters, and it's just going to kind of wander around. So we're going to start with a region around this particular point, and then we're going to calculate the mean in that region, and then we're going to shift that data point to the mean of the region. And that's why this is called mean shift. And we're going to stop when the mean stops moving. So let's watch this in action. I start with the data point, and I look at the region, and then I calculate the mean within that region, and then I shift the data point to where that mean is. And ultimately, what that's going to do is kind of draw in my data point here. It's not a data point. It's this middle point, or this point representing the middle of the cluster, to the center or the most dense part of this data set. And that's what the goal of mean shift is. All right, so how do I do clustering with this? Well, with clustering, I distribute a whole ton of these dots evenly around the entire graph of the cluster that I'm or the joint distribution of variables that I'm trying to cluster. So again, in a picture form, when I'm looking at it on like a two-dimensional graph, I'm going to distribute a whole ton of these dots, these red dots, that this is a single red dot. This whole graph is representing the journey of a single red dot. But I'm going to put a whole bunch of these red dots on a graph, and I'm going to watch them all move. And the cool part is that, if a single red dot can identify the center of a data set, well, if I put a whole bunch of them, then ideally a whole bunch of them are going to kind of go to all the centers of all these data sets and really agree. And again, to me, it kind of reminds me of a data black hole where all these dots are just falling into the black hole. So let's look at this. We have all these dots distributed out, and you're seeing the dots are slowly working their way to the center of that data. And what we see is that we have a couple of places where the dots seem to be centralizing. Now, after all the dots get close enough, we kind of look around and we just pick a single dot. And that single dot is used in, say, a k-means algorithm to then define which variables fall within which clusters. But the really cool part about the mean shift algorithm is that I don't need to pre-specify the number of clusters. What mean shift does is it says, okay, I'm just going to spread out a whole bunch of these dots to start with, and then let them fall into the centers, and then we'll just see how many centers end up coming out. And in this particular case, the mean shift algorithm, after it lets the data fall to the center of these clusters, finds 4 clusters within this data set, and then using an algorithm similar to k-means, or maybe even the exact k-means algorithm that we've discussed, defines which of the data points go with which cluster. And I say k-means, what it really is that last step of k-means where I just look at what data points are closest to which cluster center. So it's not really the whole k-means algorithm. It's really just saying, okay, this is where the which data points are closest to which of these centers. All right, well, dbScan's the last algorithm that we're going to talk about in class today. It stands for density-based spatial clustering of applications with noise. And it's a bit of a different approach, but is also pretty cool to watch work. Well, first of all, we're going to start with a random point and then see if we can build neighborhoods around it. That is, I'm going to look in a certain region and see, do you have any friends that live with you in this region? And if you do, if you have friends, if you have other data points that live close enough within that particular region, then we're going to call that a quote-unquote neighborhood. And then we're going to start building that out. We're going to look at all your friends' houses and see how many data points do y'all have within your regions. And if you have enough, then you also have a neighborhood, and all those other new data points are in your neighborhood. And then we're going to grow and grow and grow and grow and grow until we end up being done with that neighborhood, and then we go back to square one, where we start with a random new point that we haven't already classified in a neighborhood, and in that random new point, that then we see if there's a neighborhood or not. Now, what's interesting with dbScan is that while we may do the neighborhoods and start again, we might end up with data points that end up with no neighborhoods. We might call them outliers or middle points or non-classified points, but this is an interesting approach because with all of our other approaches, we could at least say with any given data point, this is the cluster we think is most associated with it, or this is our best guess at the cluster it falls in. With dbScan, we're going to end up with some data points where we say, yeah, I'm not sure that really does fall in a cluster. Now, this may be bad because we want to know what cluster to use for each of the data points. On the other hand, this may be very good if we go back to our targeted marketing scheme where we say, for these individuals who kind of fall in the middle, maybe we don't want to send them a very targeted marketing message. Maybe we want to leave that a little bit more general for these individuals who fall in the middle. And maybe we only want to do this targeted marketing with individuals who are very closely aligned with kind of this central theme of our cluster. So this can be good or bad. Either way, though, it's a very clever algorithm, and it doesn't require knowing the number of clusters beforehand. So these last couple we've talked about, mean shift and dbScan, in addition to hierarchical clustering, all don't require knowing the number of clusters K beforehand. This one is pretty interesting because it handles non-standard shapes a little bit better. That is, standard shapes, we think about groupings of data, but sometimes I mentioned like a circle within a circle kind of a deal. dbScan is going to be able to handle that better. And it really depends on your data and what you're expecting as to whether or not that matters in the first place. But in situations where that's important, among all of these, we might consider dbScan to be, for one or two particular complex situations I'm thinking of, dbScan is probably the best option to do. And again, depending on how you want it to identify those middle cases, if you want those middle cases to be left as question marks, you might prefer the maximum likelihood approach where you say they have low probability of being in any cluster, thus I declare them in the middle. Or you may prefer dbScan, where it just doesn't offer anything for those particular cases. On the other hand, where clusters are a little bit more spread, or where that definition of neighborhood, how close points have to be, is misspecified with respect to clusters spread, this can be a problematic approach. And actually, there are some additional approaches to try to build onto this, but it's something worth noting here that with clusters with more spread, this is something that can be that dbScan can run into issues with. And actually, I would say even a bigger issue probably is with clusters with very largely varying amounts of spread. So I have some clusters that are very densely packed and some clusters that are very variable, because I need to set a neighborhood definition for the entire data set. And so one neighborhood definition for the densely packed cluster might not work at all for the loosely packed cluster, and vice versa. So that differential performance is a limitation of dbScan, and again, an area of active and ongoing research. So here we can see the definition of the neighborhood, and it expands out these neighborhoods in these different colors. You'll notice now that it's trying out each of the different points in black, that it's slowly turning from gray to black, and as it turns them from gray to black, is marking them as points that don't have a neighborhood. So each of those are going to be considered our edge cases, or points that maybe aren't associated with any particular cluster. And that's because, again, we look in the circle of the neighborhood of all of the points that have that particular color, and these edge cases don't fall within a neighborhood of any of those circled points, and that's why they aren't considered to be included within those clusters. Again, this can be a good thing depending, but this also could be a bad thing depending on what you're looking for. In any case, this has been a presentation of the cluster analysis approaches and some alternate options in terms of distance metrics and alternates to the entire k-means clustering algorithm, with a few different options. These options, depending on their context, can be beneficial or detrimental in comparison to k-means, but certainly can represent some more tools in your toolbox that you can use. And hopefully if somebody mentions, hey, I used a dbScan or I used a maximum likelihood clustering approach, now you'll at least know what they mean, broadly speaking, and have some ideas. If you run into a particular case or circumstance where one of these seems to make more sense to you, be able to recall this and hopefully identify which would be the best algorithm to use in your situation.